Yo, what's up, guys? Friday, March 12th, 2021. I know that was a little more excited than I normally sound for coding problems, but uh, I am excited to bring you a coding problem. What can I say? I love coding, and it's a Friday night, so what else is there to do, right? Pandemic and all that, and well, anyway, I would have been doing this probably anyway on Friday, so that shows you what kind of life I have. Just kidding. I have a life. Yeah, whatever. Anyway, so today I'm going to be doing another quick and dirty problem. It's another tree problem. I don't know, I just like tree problems. They're like a simple baby version of harder graph problems that you come across in coding challenges, and they're good, like, introduction into how you can manipulate DFS and BFS and other kinds of recursive iteration techniques or recursive execution techniques to make your code more robust and allow you to accomplish more interesting things in faster time. Once again, without further ado, let's continue. So the problem today is Leetcode problem, and I already, obviously, I solved this problem already. So, but I'm going to go through how I solved it, and let's go back to it. And I want to just kind of discuss, the details and what I normally do. So the problem is 965 univalued binary tree. It's a pretty simple problem, I think. I think the acceptance rate was like 67%, and it was labeled easy. So this shouldn't actually be too complicated a problem. Binary tree is univalued if every node in the tree has the same value. Return true if and only if the given tree is univalued. So I mean, you're probably thinking, this is like as simple as just kind of keeping track of every node in the tree, right? And you'd pretty much be right. And keeping track of every node in the tree pretty much is as simple, I think, as keeping track of the root node, right? Because if the root node is equal to every other node in the tree, the node, and if it's of one difference, if it's equal to every other node in the tree, obviously we're good. If there's one node that's different, then the tree is not univalued, right? So we can just simply use that proof by contradiction, inductive kind of setup there to solve this problem. So first thing is, it's a tree problem, so I like to use DFS and BFS and all those good search techniques when necessary. So the first thing is we have we'll start with the root node. So this is the basic template. So what I think we'd have to do is somehow check if the root of the tree is equal to every other node in the tree, and if it's not equal, there's a contradiction. So how do we persist the root through the DFS? So that's easy. I think all we need to do is maintain a reference to the root node. Again, one contradiction will invalidate the entire tree. So let's start. If root, and by the way, since this is a true or false, we want to be able to return true or false. We're not accumulating anything. We're not looking at a list. At least that's not the strategy I'm choosing. All I'm doing is I'm keeping track of a pointer, and I'm returning immediately. I'm returning false, which will falsify everything else. One false if I AND all my recursive calls on the call stack together. So I just need a boolean for the return type. So if root equals false, root equals null, null, we return false, true, right? Because yes, if it's null at that point, recursively, that's a univalued tree. So here's the trick. If check equals null, that means this is our first iteration, right? So then check equals root. Okay. So if it's null, if check is equal to null, we want to say that the comparison node, as we persisted through the rest of the tree, is going to be the first node in the tree, right? So I'll show you in a second. Else, now, if check is not null, then check.val not equal to root.val return false. Okay, because that is, again, an invalidating condition here. This is the only thing we need to invalidate the entire recursion. Okay, so, and then what is our recursive call going to be? So we return. So if those two conditions pass, that means that we can we should go further down the call stack. So return DFS root.left, check. And remember, DFS, we are trying to root.right and then check. We're anding the left and the right recursion because essentially, again, one and to several, one falses to several ands will falsify the entire Boolean expression, and that's exactly what we want. So if so all we need to do here, I believe, is return DFS root null. And I believe that should do it. Again, I solved this beforehand, so that solves the test case, right? And then there you go. Interestingly enough, there was a lot. So the memory, the iteration is O of n, right? Because we're iterating through each of the nodes. This could be done iteratively, and that's why on my memory, presumably my memory is 40.83% of online submission, because I'm adding to the call stack. So this is log n traversal, right? A log n memory for each depth in the call stack, right? Each stack call, right? Successive stack call in the call stack. So we could do better, but that's it. I just wanted a quick and dirty problem. And yeah, if you like this video, like, subscribe, do all that great stuff. That'll get me seen. I'll be posting more harder problems as time goes on. I will also answer any questions that you have, and I doubt there would be any for this, because this is probably one of the easiest problems that you'd ever come across, whether it's in an interview or whether you're just, I mean, it's just a warm-up, really, right? So either way, see you around, have fun.